This is going to be a pretty heady discussion of potential energy versus position, force versus position, graphs and functions, how they relate to one another, and how to read potential energy versus position graphs. This, in the year of our COVID 2021, on the test, it's not going to be nearly as much detail required as what we're going to see here, but this is for posterity, so I'm going to give it the full beans. Let's start out with essentially where the lab that you're doing in the near future will have done should give you a position versus a potential energy versus position graph that looks something like this for a spring. This graph should be no surprise because the potential energy for a spring is equal to 1/2 kx squared. So we would expect a quadratic shaped graph, potential energy versus position. And this would be for a spring, which is, let's see, given these are positions that are positive, this would be for a spring that is extended or stretched. Say here is, let's say this is position 0 and it is stretched to the right. So we're talking about positive positions here for something attached to a spring. Now, of course, if you were to let go of this spring, let go of this object, it is going to spring, it's going to move to the left. And as we've talked about, like any kind of pendulum or spring object, it's not going to stop when it gets back to its equilibrium position. It's going to carry on and go past that and end up over here with a negative position. And so we could, that negative position would be a negative x, but when you square it, that's going to be a positive. And so you could picture the graph essentially being a mirror image. When you move to the left, the gravitational, the spring energy increases. When you move it to the right of equilibrium, the spring energy increases. So it's going to have spring energy on both the right and left points of equilibrium. Now, let's look at this in a little bit more detail. Anytime we look at a graph, there are really two key values, quantities that we could immediately be interested in pulling out of this graph. One is an area, the other is a slope. We've talked about area in other cases, but what's more interesting for this one, or more useful, is the slope. So if we were interested in finding the slope at a point, it would be the change in potential energy over a small change in position. So what that would tell us, now I'm not going to quantitatively dig into this, but more dimensionally, what are the units that this would indicate? So the slope of a change in potential energy over a change in position. So potential energy is joules. Change in position would be meters. Now a joule, like work, the unit of work, the unit of energy. Work is measured in joules, and work is force times displacement, force times d. So we're talking about newtons times meters. So a joule is a newton meter. So newtons times meters over meters, cancel those out. Oh, look at that. The resulting unit is newtons. So that suggests that the slope or derivative of this position versus time graph should somehow relate to a force. And honestly, that should really be no surprise, because when we looked earlier at force versus position graphs, force versus position, and we took the area inside, the area is the integral. So when we integrated a force versus position graph, the integral of a spring, for example, kx with respect to x, we got 1/2 kx squared, which would be the work done in compressing or stretching that spring, 1/2 kx squared. So that tells us something about the energy imparted into that spring. Well, the reverse process of integrating would be taking the derivative. The derivative of the potential energy with respect to position would be the derivative of 1/2 kx squared. Well, when we take the derivative, we use the power rule. So we got x to the second power. We bring that out front as a coefficient. So we got 2 times 1/2 times k times x, and we reduce that power by 1. So 2 minus 1 is 1. X to the first power is x. 2 times 1/2 cancels out, is kx. Fascinating. Kx is the force. That's the magnitude of the force. Now I say magnitude because there's one additional little detail to pick up on in this case, and that is recognizing that when you displace something to the right, let's say this is a horizontally oriented spring and you pull it to the right. Maybe left? I don't know. Cameras are reversed. If you pull it to the right, the spring itself is going to pull to the left. So the force in this case, as you have a positive displacement, the force is actually going to be pulling it back to the left. So it turns out that the derivative of the potential energy with respect to x is actually the negative of the force. In other words, the slope is the negative of the force, or you could say the negative of the slope is the force. So let's just put that into practice here. Here is a positive slope, and it's being displaced to the right. Well, if you stretch a spring to the right, the spring is going to exert a force to the left. So a positive slope is going to correspond with a negative force that the spring will be exerting. And if we look at the left side of this graph, well, at this point, it's got a negative slope. And so if you compress the spring, if you push the spring to the left of equilibrium, well, the spring itself is going to be exerting a positive force, or a force that is going to try to push it back in the positive direction. And so this, easy to overlook, but somewhat relevant aspect is true, that the derivative of the potential energy is the negative of the force. So we've got a couple big ideas that we're going to carry through. The derivative of the potential energy is, at least in magnitude, is equal to the force, and the integral of the force is equal to the work done, or is equal to the energy added. So let's put that into play in reading qualitatively a potential energy versus position curve. Basically ask ourselves, what can we tell from this curve? So we've got a potential energy of 6 units, 6 joules at a position of x0. And if we were to release something at this point, and I'm going to kind of bank on the fact that there's a very slight slope there. You know what? Maybe let's skip that. Let's release it at 0.1, or really anywhere to the right of 0. If we look at this entire region, this whole area right here, we can see that everywhere in that region between x0 and x2, the slope of the graph is negative. So just by virtue of seeing a negative potential energy slope, that tells us that the force is positive. So that means there's going to be a push to the right. Positive force, negative slope, positive force for this entire region. And if we look between x2 and x3, well, we can see that there is a positive slope in that region. So that tells us that there's going to be a positive slope will correspond to a negative force. And so if we released an object here, for example, there's going to be a positive force. That means if we release it from rest and there's a positive force, that means it's going to be propelled to the right, propelled in the positive direction. So it's going to, as you might expect, it's going to go to the right. Effectively, now this is not to say that this is a roller coaster, but the graph essentially behaves as if it were a roller coaster. If you place an object right here, of course it's going to go that way. It's going to go in the positive direction, and it's going to do that until, well, if we release it right at this point where I'm indicating right there, at rest, then this location essentially corresponds with the kinetic energy of 0. If we release it from rest right there, it's going to move to the right. It's going to gain kinetic energy on its way down. So at this point at the bottom, we're going to have essentially a max kinetic energy because that's where the potential energy has gone to 0. And as it goes up the other side, it's experiencing a negative force, so it's going to be decelerating, and it's going to continue up the other side until the amount of potential energy that it started with at point 1 equals the amount of potential energy that it started with at, well, whatever that spot is between 2 and 3. So the potential energy at this point is going to equal the potential energy that it had at the beginning, with speeding up and then slowing down in the middle. So we can kind of get a sense of which direction the force is acting and which direction the thing is going to go based on the slope of the potential energy. And we can also tell something about the kinetic energy based on where the potential energy is the least. It starts with potential energy and uses it all up. That's going to turn into kinetic energy. So let's look at that quantitatively. What is going to make a graph that looks like this? I don't know. But as we talked about just in the previous example, let's say this red line indicates the total energy that an object has. And here's the potential energy curve, this blue line. And one might ask, what's going on over here where the potential energy is greater than the total energy? Well, theoretically, that can't happen. And so, effectively, this is sort of an impossible region. That is something that can't be true. And so the object in question can't ever effectively move past a point 2. This region is sort of, the void. Now, that is that's dependent on the fact that at this point right here, and this is a way you can interpret this, the line where the total energy bar crosses the potential energy graph, you can say that the kinetic energy there equals 0. So if the kinetic energy equaled 0, then it would not have enough energy to move to the left, to go any higher. It can only move to the right. And we know that because the slope of this line is negative. Negative slope, there's going to be a positive force. So starting at position 2, it's going to be pushed to the right. All right, so at what value or values of this, of x, is this particle's speed a maximum? All right, well, in any transition between kinetic and potential energy, the speed will be the greatest where the potential energy is the least. So look for that spot. Potential energy is the least at a position of 6 meters. That's where most of its potential energy will have turned into kinetic. So at x equals 6 meters, that's where it's going to be going the fastest. Does this particle have a turning point or points in the range? Well, if it starts at position 2 with no kinetic energy, and according to the slope, it's going to have a force pushing it to the right, it's going to proceed to the right. It's going to maximize its kinetic energy right here at 0.6. Okay. max. And that kinetic energy will progressively turn back into kinetic potential energy as it makes its way further and further to the right until it reaches this point where it runs out of kinetic energy. The total energy is equal to the potential energy at that point. We're again reaching a moment where the kinetic energy is zero. So the maximum position it can reach going to the right is 8, the position of 8 meters. If the total energy is changed appropriately, could the particle remain at rest at any point or points covered by the graph? If so, where? So what we got to imagine here, I'm going to erase a bunch of stuff, is we imagine that total energy bar, this red bar, could be moved up or down. Well, I can do that. I'm going to move it down. Let's see. I move it to right here, say. Well, if we moved it to here, then this and this, like if it was in between those points, it would never get out because it would only be able to move to the right and to the left, but it would never achieve enough energy to get over the hump or to go further to the left than position 2. So if we continue to move that graph, that bar down, that total energy bar down to a point where it in fact coincides with the lowest point on the graph, essentially, if the potential energy and the total energy are equal at a valley, basically you're saying you're in the bottom of the valley and you've got no kinetic energy. Well, then you're stuck there. If you're at the bottom of the valley and you've got no kinetic energy, you're stuck there. So it could happen at point 3, or if we continue to lower that total energy, it could happen again at point 6. So x equals 3 meters or x equals 6 meters, depending on how much energy you take away from the system. All right, so there's a little bit of mildly quantitative graph reading. Now let's bring in the heavy stuff. So a particle of mass 2 kilograms is free to move along the x-axis. The particle's potential energy is given by this interesting function where x is position in meters and u is energy in joules. The particle begins at rest at the origin. So at the origin position of 0. This axis, the horizontal axis, is position. Horizontal axis is position. So I used Desmos to graph this function, and this red function is the potential energy function. Maybe I'll use red for that. Potential energy as a function of x looks like that. So this graph, this function is that. And I used, again, Desmos to take the derivative, as we said. The derivative of the potential energy graph with respect to x is the negative of the force. Or maybe I'll put the negative over there, is the force. So I graphed the derivative of that function. Now, just for thoroughness sake, let's actually take the derivative. The derivative of the potential energy function with respect to x would be the derivative of x cubed minus 3x plus 3, all with respect to x. Power rule says that's going to be 3x squared minus 3. So the force, and it's negative. We've got to take the negative of that. So the force is going to be negative 3x squared minus 3. It's going to be a parabola, and it's going to be negative, so it's going to be an upside down parabola. Parabola facing down, and that's exactly what that looks like. Let's shrink that, stick that up there. So we've got graphs of curves U and F. We've got a potential energy graph, and we've got a force graph. Determine the particle's maximum speed. All right, well, we said that this particle is released at rest at the origin. So I'm going to draw a red bar across here to indicate total energy, because at this point, kinetic energy is 0. And so at that point, the entirety of the energy is going to be potential. So basically, everything to the left, all this region over here, this pretzel area, is not accessible under these circumstances because we're giving it no kinetic energy at the origin. It's not going to be able to go up the hill. It's only going to be able to go down the hill. So this force, another way we can tell that is that this slope is negative. Thus, there's going to be a positive force, a force pushing it to the right. So when we release it at 0, it's going to be pushed to the right. Determine the particle's maximum speed. All right, well, let's think about how this works. If you start with potential energy and that turns into kinetic energy, the question is, how much kinetic energy are you going to get? Well, we can tell that by looking at our graph. How much kinetic energy are we going to get? Well, according to this graph, we start with an initial potential energy of 3 joules, and according to the graph, we end with a potential energy of 1 joule. Well, that equates to a translation or a transformation of 2 joules of kinetic energy. We've lost 2 joules of potential, so 2 joules has turned into kinetic energy. So for part B, our kinetic energy is going to be 2 joules. So that's going to be 1/2 mv squared. It's a 2 kilogram object. I think that was chosen intentionally. So we get 2 equals 1/2 times the mass of 2 times v squared. All right, so that cancels. So v equals the square root of 2. V equals 1.41 meters per second. Determine the particle's greatest departure from the origin. All right, well, that total energy bar becomes useful again because it's going to move. This object is going to have the opportunity, the ability to move as long as it has kinetic energy. And as we've said, the point or the locations where the potential energy bar or potential energy graph crosses this total energy bar indicates the points where there is no kinetic energy. Kinetic energy is 0 there and there. So it's going to move to the right until it runs out of kinetic energy, and that position at the right corresponds with about that location, approximately that location. Now, how do we solve that mathematically? Essentially, we are recognizing that the potential energy is 3 joules. So we want to solve for x positions where potential energy equals 3 joules. So for part C, we can say potential energy is potential energy at x. Well, it is that function equals x cubed minus 3x plus 3. We're going to set that all equal to 3 joules. We want to find the locations of x that correspond with that amount of energy. Given that that is a cubed function, gets a little annoying, I would do that on a calculator and say so. Done on a calculator, we determined that x is going to be, 0 is going to be one of the roots, and 1.73 is going to be another. And we're also going to get another negative root way over here, but we already know that that's out of bounds, so we're not really worried about that. So 1.3 meters is the answer that makes sense that we're looking for. Determine the particle's maximum rate of acceleration. All right, in either direction. Okay, so we've already identified the fact that it's not going to get past 0 and it's not going to get past 1.73 meters. So if we're interested in the acceleration, we need to know something about the force. Well, so part D, we've determined that the force is equal to negative 3x squared minus 3, and we want to find the force at 0 and 1.73, because those are the maximum locations. You can also tell that from the graph, that's where the graph is the steepest, both here and here. I think you could tell just by eyeball that it is actually the steepest at 1.73 meters. So that's probably going to be the location of maximum acceleration. But for thoroughness, let's just do both. So the force at 0 is going to be 3 times 0 squared. Negative 3 is going to be 3. 3 meters per second. Nope, that's going to be 3 newtons. All right, so the force at location 0 is 3 newtons, and the force at 1.73 is going to be negative 3 times 1.73 squared minus 3, close paren, 1.73 squared times 3 minus 3. The opposite of that is 3. Oh, fantastic. The force at 1.73 is, interestingly, also 3 newtons. I'm surprised by that. What did I not do? Got position of 1, position 0, position 1. Oh, you know what I didn't do? I didn't take this graph far enough. So if we took that graph a little bit further and see at position 0, oh, there is a force graph here, by the way. At position 0, the force is 3 newtons. And at a position of 1.73, we continue this graph, turns out that is negative 3 newtons. Oh, I lost a negative somewhere. Negative 3 newtons, which makes sense because as it moved to the right, it's going to get pushed back to the left. So at either of those locations, the force is 3 newtons, and F equals ma. So the acceleration of this, what is it? 2 kilogram object is going to be the force, 3 newtons, divided by the mass. 2 kilograms is going to be 1.5 meters per second squared. I think I didn't answer that question correctly. I mean, I think I answered it correctly. I think the answer given is incorrect. It's going to be 1.5 meters per second squared. Describe the overall motion of the object. I think we've kind of covered that, but it's going to start from rest at position 0. It's going to experience a force to the right in the positive direction. It's going to accelerate. It's going to accelerate until it reaches position of 1. That's where the kinetic energy is a maximum. That's also where the force becomes 0. So at that point, it's going to experience a deceleration. It's going to slow down and it's going to stop at a position of 1.73 meters and then come back the other way. Oh, we're really getting into it. And the last couple of questions, let's shrink these down, get those out of the way. The last couple of questions. What initial speed would be required to prevent the particle from returning to the origin? How would we do that? To prevent it from returning to the origin, well, if we look at our graph, let's get rid of all this nonsense. Basically, what we're saying now is we're going to give it some kinetic energy, or we're going to allow it to have some kinetic energy, which is to say the total energy at this point is not exclusively potential. Basically, what that means is we want to know how much energy it's going to need in order to, well, if it was going to move to the right, if we let it move to the right and gave it some kinetic energy, it would go this way. But you might see or might notice that that graph really just continues up to infinity in a positive direction. So What was the question? Prevent the particle from returning to the origin. Right. So if the potential energy graph goes up to infinity, there's no amount of kinetic energy we could give it to get past a hump. There is no hump going to the right. There is a hump going to the left. If we give this thing a strong enough push to the left, then it will go up the hump. It will get past this point of maximum potential energy. It will go over the other side, and it will never come back because the other side of this graph, it drops down to negative infinity. So the question really is, how much energy do we need to give it so that it can reach the hump, so that it can get up to the hump and have anything greater than zero kinetic energy? Well, the energy gap, or the energy need, the kinetic energy it would need to have is, well, it's got 3 joules of potential energy there, and it needs to achieve a position where it has 5 joules. That means the missing kinetic energy needed would be 2 joules. So for part D, E, F. For part F, the kinetic energy needed to get over the hump would be 2 joules, and that would be equal to 1/2 m, the mass, which is 2, times v squared. And so we get 2 equals v squared. Oh, that's familiar math, coincidentally. It just works out the same in this particular case, that the velocity needed with, if it had that velocity while going to the left, it would make it over the hump, which would be 1.41 meters per second squared. Although now it occurs to me, you could push it and have it go to the right. And if it did, it would go to the right. It would get yay high and then come back and go yay high and then carry over to the other side. So actually it doesn't matter which way you give it a push. If you give it an initial velocity at 1.41 meters per second, it's going to have enough to get over the hump and then carry on the other side. And lastly, if the particle is given the speed 3 meters per second at the origin, what will be its speed at a position of negative 3 meters? All right. So, we already have its potential energy. We know that potential energy goes as a function of, what was it? X cubed minus 3x plus 3. So what we're saying is it's going to have this amount of potential energy. The total energy will be the potential energy plus the kinetic energy. And we want to know what will be its speed at x equals negative 3 meters. One thing we know is how much potential energy it has right here. It's clearly at 0.0, it's got 3 joules of potential energy. So at total energy, the energy at 0.0 is going to be however much potential it's got plus however much kinetic it's got with this original speed. So that would be 3 joules plus 1/2 times the mass, 2 times, it's going 3 meters per second, so that's going to be 9. So it's going to have a total at position 0, total energy of 12 joules. Now that energy is going to be constant everywhere. It's conservation of energy. So we need to know how much potential energy it's going to have at the position of negative 3 meters, because the energy total at 0.0 is going to be the energy total at negative 3 meters. So that's going to be the potential energy at negative 3 plus however much kinetic energy it's got. So we need to know the potential energy at negative 3. So let's plug in negative 3 for that function. So that's going to be negative 3 cubed minus 3 times negative 3 plus 3. Did I get that right? I think so. plus however much kinetic energy there is. So the grand total of energy, 12, is going to equal that plus the kinetic energy, which is going to be 1/2 times 2 times v squared. So -3 cubed is -27 minus 3 times -3. So it's plus 9 plus 3. So we got 12 equals -27 plus 9, that's -18, plus 3, that's -15, plus v squared, add 15 to the other side, so we've got 27 equals v squared, take the square root of that, 27 square root is v is going to be 5.2 meters per second. Oh boy, it's heady stuff. I'm not going to ask you in the year 2021 to dig in that deeply on a problem like this, but if it's 2022 or later, you're in for it. Let's go. Thank you for your attendance.